So now we have Darko Marnov, and he wins the longest title award.
Okay, that's good.
Did you know that? Hopefully you won't win the longest talk award, too.
Make it shorter for lunch, right?
Yeah, we're hungry. Okay, so he's going to talk about some, well, I'll let you talk about it, but explicit state model checking for dynamic allocation.
Okay, thanks. Yeah, I'll be talking about something as John said. The thing was, I actually asked him what we should talk about here, whether it should be a talk accessible to a more broader audience or just some research talk. Said that it's fine to go with the research talk. So what I'll present basically is something that my student Steve Lauterberg presented at ICSI last month. And just one piece of paper. It's nothing broad. It's definitely not on software testing. It was originally announced in his talk. So it doesn't have much to do with testing. It has actually to do with model checking. So basically, I'll be talking about the state space exploration, which is the basis for model checking. It can be used to find bugs or verify certain properties. Basically, what it does is that it systematically explores a program state space. So a lot of research in this area has focused actually on speeding up this state space exploration for a single given version of a program. All these techniques like partial order reduction, symmetry reduction, and so on. And we've seen Tefik presented some work, say, on modular checking. The idea always is that you're looking just at one given version of a program and you want to test or check that version. However, in reality, the software evolves. So it's not that we have only one given version and the fixed version, and that's the one we want to check. But actually, software goes through various versions, and we have to repeat all these validation activities for these versions. In some sense, all these costs accumulate over time. And reducing actually these costs across the entire evolution is an active topic in research. Say for something like regression testing, there are a lot of techniques being developed and explored. In this area, things like regression test selection, safe test selection, test prioritization, impact analysis, creating unit tests from system tests, and so on. So the main idea here is that in regression testing, you're going to run a number of tests across the versions of a programs. So instead of running all the tests at once, how can you achieve some savings by, say, running only a subset of them or maybe reordering them to run them in a different way and so on. So that's in domain of testing. And Colin was also presenting some way in which you can try to also save some time if you are doing some kind of verification across versions of the program. How can you reuse the results from one verification, one checking for another? The question that we asked in this specific work was whether model checking costs for this evolving software can be somehow reduced in a similar fashion. And there has been prior work on that, came under the name of incremental model checking. There have been several techniques proposed for that, ranging for various formalisms and so on. Some of the more recent work on extreme model checking. There has been also some practical importance of that argued. It was this paper by Sisla basically saying that if these techniques are to be adopted more widely, then they more or less have to work in this incremental fashion. Otherwise, it may be too slow to run them over and over again from scratch. But all these previous techniques mostly focused on control-intensive properties. What I mean by that is some kind of the examples that we've seen again in the Tefik's talk. Basically, if you have some kind of state machines and you want to check that your code goes through these states in a proper way. So these techniques did not handle well some complex data. So what we want then to do in this work was to specifically focus on such data. So our goal was to speed up the state space exploration for evolving software that does have dynamically allocated data. So even more specifically, we wanted to focus on explicit state model checkers for actual programs and data-intensive properties. So more or less here you can think Java, PathFinder, or JPF. That's where we also did our implementation on. And these things are important because these kind of tools are used nowadays. They're used to find bugs in some real programs. They're also used to generate tests and so on. They've been shown practical in a number of situations. Here's just a partial list of some of these tools that people are actually using. So here's then basically how the talk will proceed as a standard conference talk, just some example that illustrates this technique, some key observations about the state space explorations, specifics of our technique, some experimental evaluation that we did, and just conclude that. So here's the example. Suppose that we have this class, kind of similar to the hash table class that we've seen, but here it's a bit different. We have this binomial heap class. It implements the heap interface using these binomial trees, binomial heaps. And the key point here is that there are some nodes that are linked in some way. They contain some values. But there are these two methods that we have for these values. We can insert an element into the heap, so we can add a value, or we can extract or remove the minimal value from the binomial heap. Suppose now that you want to check this implementation using something like a Java PathFinder. Well, what we can do is explore the state space of this class. So what happens if you create an empty heap and then start inserting some values and removing, what kind of states are we reaching and whether they're all correct or not. Here I'm just going then basically to explain how standard state space exploration proceeds. So the goal here is to introduce certain terminology that I'll require to describe our technique. For those of you who know these things, it's just quite the standard way that any explicit state model checking works. So the idea is that we start from some starting state. In our case of the heaps, we'll start from an empty heap. So it just has the size 0. There are no values in there. And then we want to choose certain method to apply. We want to either insert values 1 or 2, say, or extract the minimum value. In this particular exploration, we are going to limit this depth to up to 3 method calls. So we are going to see only what happens with the states of this heap if we apply up to 3 methods. And the values for these insertions will be only from the set 1 and 2. Generally, there is also some property phi that we want to check on each of these states, but that won't be discussed here. So we need to choose certain transition. Then we need to execute this transition and obtain a new state. So say if you're inserting value 1 into the heap, we are going to get a new heap, which now has the size 1. And there is one node that stores this value 1. Because we are talking about these complex data and the actual execution of the code, the point here is that this execution can take a lot of time. Of course, clearly inserting just the value 1 into a small tree is not going to take the time. But in general, if you're simulating something bigger, if you're talking about network protocols and you're executing some action there, this can take a lot of time. It's a difference from, say, model checking some of the hardware things where the execution itself may be very fast. So because we are talking about the software, the execution can be quite costly. Then for this new state, we can check the property phi. And then we can compare whether we've already seen this state or not. In case that we've seen the state, we want to stop the exploration. In order to do that, we keep this set of visited nodes. Basically here, we keep the set of all the nodes that we visited before of those states. And usually we hash that. So this would be some hash value of the initial state that we had there. In this case, we get a new state S1. We haven't seen this one, so we add it to the visited set, and then we continue. So we need to backtrack. We need to explore another transition. We obtain new state, continue in this fashion. So here, when we execute this, extract the minimal value from this heap, because the heap is empty, it will remain empty. So we've already seen this, and we'll stop the exploration for this particular path. So effectively, we are just getting a back loop. Then we restore this state, and again, continue this exploration. See that we are obtaining some states. We proceed in this fashion. Eventually, this is the entire state space that we obtain in this case, because we've limited everything here. This is a finite state, so we can finish the exploration. But the key point here is to point out that there are different transition types. If you look at this state space, there are actually a number of ways in which we can reach the state, and we distinguish between these 3 types. There are these 3 transitions, which are marked here in blue. And what they do is actually they get us to a new state. There are also non-tree transitions. They're marked here in red. There are 6 of them. What they do is they're actually some kind of loop. So we are either going back into a self loop, into a state that the state itself, or we are going back to some state that we've seen previously. Also some of these deepest transitions. Deepest means that we are at the end of the exploration. We specify that we want the depth to be 3. So when we execute the 3rd method, we know that we are reaching the end of the exploration. In this case, this happened to be going back to some states we visited, but that's not necessarily true in a general case. So now the question that we can ask is, suppose that we make some change in this code. We've had this class. We've asked some undergrad to implement binomial heap. We've checked that. Suppose that there was some bug, and now we ask this student to go make a change in the code. Now, the change that's made is typically going to be fairly small. So suppose now that we want to check the new version of the code, is it really necessary to redo all the work from scratch? So suppose that we just change the extract min method, and using a traditional state space exploration, we would really need to do this again from scratch and explore everything. So we need to execute all the transitions, we need to do all the property checks, all the state hashing computations, state comparisons, and so on. Indeed, if we change the extract min, this is what we do have to do for the extract min. Unless we know some more information about how the change was performed, if we don't know anything, we just know that there was some change, we really need to execute that. However, is this really necessary for add? Well, as it turns out, this is not necessary for add. Many of these changes that are made do not actually affect all the transitions in an exploration. So if a transition was not modified, if we did not change the method add, then often we do not need to actually execute even this method add, and we do not need to check what happens with the new state. The code remains the same, therefore if we execute it on the old state, we know that it's going to get to the same state we've seen before, so we can avoid a lot of these executions, comparison, and so on. So we can significantly reduce cost by reusing some of these checks. And that's indeed what we propose. So we propose a technique that we call the incremental state space exploration, or for short, ISSE, which basically exploits this information about the prior exploration to reduce the cost of the current exploration. So it reduces the number of these executions, the transition executions, and also it reduces the number of all these post-processing, so the state comparisons, the property checking, and so on. Here now I'm going to explain how this technique works, and I'm going to use exactly the same example with binomial heap, and we are just inserting values 1 and 2, and want to explore this up to depth 3. The way that this technique works is that it will use some additional information. So regular state exploration basically just operates on these states and keeps track of this set of visited states. Our ISSE is also going to keep this what we call input and output. Input actually comes from a previous exploration, and output will be the information for the next one. In our example, if we are starting this initial exploration, we don't have anything in the input. So effectively, input is empty, so we can ignore it now. So now what we are going to do is we are going to perform the exploration as before, as in the traditional case, but besides just keeping track of the visited states, we are also going to remember the entire explored state. Basically, the output structure will have information about the explored state space. So we start the execution as before, we execute add 1, this creates in some new state. What we do now in this output, we remember basically this information. That going from the initial state of the empty tree and executing add 1 leads us to the state that has now this value 1 in this heap. We do the same for add 2. Then there is this extract min, so we remember that there is some self loop there. And basically we continue this exploration to the end. Now this is done as before, very traditional exploration. However, the only additional information is that we keep track of this output data structure. Basically we build all this information, the entire graph. Of course, in some encoded version, not directly as shown here. This is just the illustration purpose. So now that was the initial exploration. So basically, we want to do incremental checking, but the first time we check some program, there is no prior information to use, so we had to do everything from scratch. Suppose now that we do make some change. We've done one exploration, we have all this, the previous graph, and now say we go to change the extract min method. For the sake of the example, we are just going to assume that it's changed, all its code is going to remain the same. It will still have the same transitions. Of course, our checker does not know that in advance. So it will need to execute this to check what's happening. However, what it does know in advance is basically this thing here, which now constitutes an input data structure. So this is the graph from the previous exploration. We know that in the old one, when the add and extract min had some previous versions of the code, this is how the state space looked like. Our goal now is to check what happens with the extract min being changed. So we start then the exploration as before. We start from the empty tree. We want to empty heap. We want to insert the value 1. We first check in the input structure whether we already have information about this transition. In traditional state space exploration, we wouldn't have any of this input. We would simply go and execute. Here, before executing, which is quite costly, we make this quick lookup into the input data structure and ask, do we have already information about that? Here we do find that when we execute this add one onto that empty heap, it's going to result in some new state, h of S1. So what we do is basically here check that we don't have this h of S1 in the visited, hence we need to execute this, and we need to build this new state. So we execute that. We do the similar thing for add2. Again, we know that there is some information there. We're going to get this S2, but we haven't seen it in the current exploration, so we need to execute that. Now, when we go to execute extract min, this operation has been changed. So we don't even look up in the input because it has been modified. Therefore, we have to execute that. So we are forced to execute there. Then we continue this exploration. Now we are going to execute add1 on the state S1. Well, add wasn't changed, hence we can look up into the input. What we do find now is that when we execute add, this was a loop previously. Therefore, it's going still to be a loop because the code for add didn't change. We've seen this already here in the visited. What we can do is avoid this execution altogether. So what we do just is we know that in this current exploration, this is going to remain the self loop. And this is really the key point, that instead of executing this and doing all the post-processing with that, we just do a quick lookup into this input data structure. Then we proceed in this fashion, and here's the entire state space that we obtain. And using this approach for incremental state space exploration, actually, in this example, we achieved the following reductions. We avoided executing 5 out of 12 transitions, so we didn't execute them at all. We didn't make 8 out of 12 property checks, and also we didn't make 8 out of 12 hash computations. So had we not used the incremental thing, we would have needed to execute all these edges shown in this graph. Also, while we were doing this, while we were reusing this input from a previous exploration, we were also building this output data structure for the next one. Here's then the crux of this, the algorithm of how it works. If we have a given state and the transition, the first thing that we ask is whether this transition was modified, whether the method was modified. If so, we do have to execute it and to have all this post-execution. If not, then there may be a chance that we can reuse this result. So for that, we have to ask whether we've seen already this in the previous exploration, whether it's in the input. If not, we have to re-execute everything. If it was, then there is some saving that we can achieve. If this is the last iteration, if that's the deepest iteration, then we can just save everything. So that's the yes branch where we don't need to do anything. However, if this is a state that we haven't seen before, we still need to execute it only. So here's some formula that basically shows some analytical results for how much can be saved. For the sake of not being late for the lunch, I'm going to omit the details of this stuff. It's just basic analysis saying what are the savings that can be achieved. I'm going actually to proceed to the empirical evaluation that shows what the numbers show and how much time we were able to save using this technique. We've implemented this SSE technique in 2 model checkers, JPF and something called JSIM, which is just specialized for network protocols. I'm going to show some of the results for both of them. So for JPF, we've first done a limit study. So the goal of this limit study was not to measure how much time gets saved if we actually make some changes, but just to do some limit study to see how much time could have been changed if we actually do not make any change. So we are just here measuring, how good the technique can be in theory without doing the actual modifications. So here are the results that we obtain. So this is for a number of benchmarks that we did. So for each of them, we have here 3 bars. The first bar, this is in yellow. This is called initial. It shows how much overhead our technique has. This is compared to the traditional state space exploration that just does the things as always. We do have some overhead because we need to maintain these input and output data structures. So if you just do the very first, the initial exploration, we are going to have some overhead, but that's relatively low overhead. What the green one shows, this is the best case. This is where we label that nothing in the code changed. Of course, if you didn't change the code, you wouldn't be even rechecking that. But just for the sake of the limit study, we just said that nothing changed in this code, and then apply this checking algorithm to see how much time it saves. As we can see, it saves sometimes from up to 20, 25%, but it goes up to over 90% of the savings that it can achieve. And then the worst case is if we label that everything changed. Again, the point here is that we want to measure what is the overhead of our technique. Even in that case, it gets up to 15% or so. So here then basically this is the overhead. This is when we do have some slowdown. It ranges between 1 and 15%. And this is when we do have a speed up. It ranges between 20 and over 90%. So besides asking the question about the time, how much time gets saved, it's also interesting to see how the memory changes. And as we can see here, using our technique, SSE, there is some more memory required. So what this graph shows is the overhead of our technique against the traditional state space exploration that doesn't reuse any results. We can see that in most of the cases, we get about 50% more memory. However, in the case of the file system, we require much more memory. So we require like 3 or 4 times more memory for doing this incremental fashion. However, that happens to be also the example where we achieve the largest saving. So for file system, we have over 90% saving there. So now, besides doing the limit studies, we've also done some experiments with the actual code evolution. The way that this worked is we would just ask some undergrads to go and implement some code, and then we would get their versions. Sometimes there would be bugs there, so we would tell them where the bug is. They would go and correct this bug. And that's how we basically build the versions of the code to be used for the experiments. And then here the results showing again, comparing our techniques against the traditional one that does everything from scratch, and showing how much our technique can save time. Basically, if you do this incremental checking, the savings that we can achieve ranges up to 62%. Sometimes there is some slowdown, in that the case of the heap array A, there is some slowdown there of about 5%. We've also done these experiments in this other model checker, JSIM State Space Explorer, which focuses on network protocols. And we obtained similar results that the savings of the memory the savings in time that we can achieve ranges up to 60-70%. Oops, sorry. Ranges up to 60-70%, and there are some certain slowdowns of up to 4, 5, up to 10%. Also, the memory shows some increase, but somewhat smaller, just because of different implementation of JSIM and JPF. So to conclude, we basically proposed this technique called ISSE, Incremental State Space Exploration. What it does is focuses on these transition executions, which are costly in software, and it tries to reduce the number of those, and also eliminate some number of these property checking. So it was implemented in 2 model checkers. It was evaluated for a number of these program explorations. And we've shown that in most of the cases, we obtained a speed up, sort of roughly about the 2 times. And there's 2 cases where there was a slowdown, but it was relatively small. So in summary, it means that this technique one can use always. So you wouldn't necessarily need to choose between the traditional or this one. But in theory, you could use this technique at all times. Okay, finishes the talk. Questions?
To which extent is your method dependent on the way to determine whether there actually has been some change? So if you change a method, then you have to change that method, but this might have ripple-on effects, and other things might. So this might cause maybe other model checking activities to find out what has been changed.
Okay, that's a good question. So basically, the question is maybe even how we find what change and which of the transitions are affected by which method. So for the sake of doing this experiment, this was all done manually, basically just by labeling that. So that's part of the future work, is basically to automate identification of these modifications. But all these techniques in impact analysis that effectively do that and find, what is the change that was made and which of these executions it can affect and so on. But it's definitely a good question, because one method can call others, right? Helper methods. So if you change the helper, you would need to find transitively what invoked what and so on. There's also the impact analysis that's done at the level of the basic blocks. Namely, even if you make a change in a method, it may not affect all the executions of these methods. You may be changing only one of the basic blocks, yet your transition only explored some other ones. In that case, even though the change was made at the method level, you would still not need to explore this same transition. So there are some trade-offs there, basically talking about the granularity of the change. That's part of the future work.
So do you know why you got a slowdown in some cases?
Yeah, the slowdowns come because the technique keeps track of these additional data structures, those things called input and output. So effectively, it remembers the entire space graph that was explored, and that just requires more memory and more time to maintain. That's why if that never gets reused, then you would always get this overhead. But as I showed you, the overhead is fairly small, between 0.5, 10%. So the overhead is not all that big.
So, I mean, was it the size of the examples that caused the overhead to go up, in some different proportion? Or, what was it about the examples that had slowdown that made them different?
The examples that had slowdown, all these slowdowns are fairly small. I guess they don't differ much. I would not know exactly about the time, what affected the time. What I know is about the memory. For example, one can ask, why is there so much more memory required here for this file system? And the reason there is that the number of outgoing edges from each state is much larger. So this sort of the fan-out, the number of transitions that you can apply at the given state is much larger. So what this file system does is things like, you create some directories, then at each of them you can create new directories, subdirectories, delete them, create new files, read, write files, and so on. So in that case, the number of transitions you can apply is much larger, and therefore the graph that you're obtaining is going to be proportionally larger than just the number of states that you have. That's why there the speedup was the largest. On the other hand, as I mentioned, what this means is that there is also the most potential for reuse and for saving time. So here we obtain also the largest saving in time. But effectively what this technique does is trade-offs memory for time. You just save more memory, you save more information from previous exploration, and you hope that to be useful in the next one to save you time. Okay, lunch.
Thanks.